Good morning, students. Now we learn this is current carrying loop placed in a uniform magnetic field. Because already previous classes we already learned, we completed few important questions, few 5 marks essay questions. But this part is the last part of the moving charges. So once you see the current carrying loop placed in a uniform magnetic field. See here I am taking one loop. That loop I am giving you name A, B, C, D. A, B, C, D is the loop which is placed in a uniform magnetic field. Now in that one, the current I is passing. Current I is passing, and this side AB and CD, AB, CD I am taking as a length L, and BC and AD I am taking as a breadth B. This I am taking, this one and this one I am taking as a length, and BC and AD I am taking as a breadth. So these two are lengths and these two are breadths. Now if this loop, if it is placing in a uniform magnetic field, now we already know when the current carrying conductor is placed in a uniform magnetic field, and definitely it will experience a force. Already in the starting part we already know a few formulas. First I am recollecting those formulas. If the charged particle is entering in a uniform magnetic field, the force experienced by the charged particle is given by F is equal to BQV sin theta. And similarly, a current carrying conductor which is placed in a uniform magnetic field, that current carrying conductor also will experience a force. That force is given by F is equal to BIL sin theta. Now we have to depend completely on this. F is equal to BIL sin theta. Now here also this rectangular loop I am considering as a 4 conductors. AB is the one conductor, and BC is the other conductor, and CD is the other conductor, and DA is the conductor. Now if such a conductors, if such a loop, if it is placed in a uniform magnetic field, and definitely those 4 conductors will experience a force, but the direction of force is different. Now see the first conductor, this AD and BC, these 2 conductors are experiencing a force, but these forces are acting, one is upwards and another one is downwards. This is upwards and this force is acting downwards. So because of here AD and BC, these 2 conductors experience a force, but these 2 forces are equal and opposite. So that is the reason these 2 forces will cancel out with each other. And similarly, the conductor AB and the conductor CD, here also, here the force is acting vertically upwards, here the force is acting vertically downwards into the plane of this board, because one is acting vertically upwards and here the CD is acting vertically downwards to the plane of the board. So that is the reason one is acting vertically upwards and second one is acting vertically downwards. So that is the reason these 2 forces constitute a torque. What we already know, torque is nothing but either of the force into perpendicular distance. Now that is the reason here, out of these 2 forces, the force which is experienced by AD and force which is experienced by BC, these 2 forces are cancelled with each other because of equal and opposite. But the force experienced by AB and the force experienced by CD, that forces we have to consider, because one is acting vertically upwards and second one is acting vertically downwards, and they are constituting a torque. Now what is the torque? First we write the force equation. F is equal to BIL sin theta. F is equal to BIL sin theta, and here the length of the conductor length of the conductor and the magnetic field, if the both are perpendicular and theta is equal to 90, so that is the reason here you simply will get F is equal to BIL. This I am taking as equation 1. Equation 1. Then what is the torque equation? The torque tau is equal to either of force into perpendicular distance. Either of force into perpendicular distance. Now here I am redrawing the diagram. This is the AD. This perpendicular distance I am taking. This perpendicular distance I am taking. This is N. Now this is the N and this is the magnetic field B bar. The angle between them is theta, and this you can take it as a B. Now here according to this theta, sin theta is nothing but opposite. Opposite is nothing but dN by AD, or dN is equal to AD sin theta. dN is equal to AD sin theta. Now what is the value of AD? AD is nothing but B. So finally dN is equal to B sin theta. So this I am taking as a equation 2. Now once again see the triangle. This is AD, and here dN stands for perpendicular distance. Perpendicular distance. Now from this triangle, sin theta is equal to opposite to hypotenuse dN by AD, or dN is equal to AD sin theta, or dN is equal to, in place of AD I can substitute B sin theta. Now substitute the perpendicular dash value and either of the force value here. Now torque tau is equal to, either of the force is nothing but BIL into perpendicular distance is nothing but B sin theta. Now length into breadth is nothing but area. Now torque tau is equal to BIA sin theta. So this is for one loop. If n number of loops are there, now the equation will be torque tau is equal to NBIA sin theta. This is for single loop and this is for n number of loops. So torque tau is equal to NBIA sin theta. So once again, all of you see the explanation part. If the current carrying loop, so far, if the charged particle enters into the magnetic field, how much force it experiences? When the current carrying conductor, if it is placed in a magnetic field, how much force it will experience? That thing will end. But now we are placing one loop. It is just like a square loop. If we are placing the square loop in a magnetic field, then how much torque it will experience, that we are finding. Now here I am taking ABCD is the one square loop. If it is placed in a uniform magnetic field, then each conductor, each part will experience a force. AB, BC, CD, DA. AB and CD are considering as a length, and BC and AD is considering as a breadth. AB and CD are considering as a length, and BC and AD is considering as a breadth. Now AD and BC, these two conductors experience a force, but the force AD is upwards and the force experienced by BC is downwards. So that is the reason these two are equal and opposite. That is the reason they are cancelled with each other. And the force experienced by AB and CD are, one is vertically upwards and the other is vertically downwards. So that is the reason they are constituting a couple. So that couple, F is equal to BL sin theta, theta is equal to 90, F is equal to BL, and torque tau is equal to either of the force into perpendicular distance, either of the force into perpendicular distance, and here the either of the force is nothing but BL into perpendicular distance. We can calculate from this diagram. So that is B sin theta, and later of substituting we got torque tau is equal to BIA sin theta. For n number of loops, torque tau is equal to NBIA sin theta. So for problems point of view, everybody must remember this final equation, because the explanation part is not necessary, but you have to remember the final formula, because for the problems point of view we have to know. Next, current loop as magnetic dipole. Current loop as magnetic dipole. What is the meaning of this heading? The current carrying loop, does it behave like a magnetic dipole? Magnetic dipole means one is acting as a north pole and another is acting like a south pole. Whether it behaves like a magnet or not. So that explanation, the confirmation we can get from this concept. Now for this one we have to recollect the magnetic field due to magnetic field along a axial line due to circular loop. Magnetic field along axial line due to a circular loop. For that one I am recollecting the formula. B is equal to mu naught by 4 pi 2 pi ni r square by r square plus x square whole power 3 by 2. This is the equation. This is the equation we got from the question. Once again, B is equal to mu naught by 4 pi 2 pi ni r square by r square plus x square whole power 3 by 2. See, this is the concern diagram for the question. And finally, after this diagram and the derivation, and finally we got this equation. B is equal to mu naught by 4 pi 2 pi ni r square by r square plus x square. Now here, in this diagram, suppose if the axial distance x is much greater than r. If the distance x is much greater than r, then we can neglect this r value. That's how the equation becomes, you see, B is equal to mu naught by 4 pi 2 pi ni r square by, it will be x cube. It will be x cube. Now, in place of this equation, suppose if it is I am taking as a one loop, then in place of n, it is equal to n is equal to 1. N is equal to 1 and m is equal to, I am taking I into pi r square, pi I into pi r square. Then substitute these two terms in the above equation. B is equal to mu naught by 4 pi into 2m by x cube. This equation is similar to what you have learned in the first chapter, electric charges, where the electric field due to electric dipole along axial line along equatorial line, where the equation we got B is equal to the constant here you will get here 2p by d cube you will get for axial line. For equatorial line you will get E is equal to constant into p by d cube you will get. So this one and that one are similar, but in place of p here we are using the term m. What is that m stands for? The m stands for the magnetic dipole moment. How we can define this magnetic dipole moment? The magnetic dipole moment is nothing but m is equal to product of current into area, or m is equal to I into, we can write it as a pi r square. So this product of I into area or I into pi r square, and this we call it as a magnetic dipole moment. What are its units? Its unit is nothing but ampere meter square. Ampere meter square is the unit for this magnetic dipole. So from this one, so this circular loop is behaves like a dipole, magnetic dipole. Then how can you know the direction? See here, if you are observing the loop, if the current is passing clockwise, if the current is passing clockwise direction, current is passing clockwise direction, then that phase is behaves like a south. Suppose in the loop, if the current is passing anti-clockwise direction, and that phase is behaves like a north pole. So once again, if you are observing that circular loop on the top of the portion, if the current is clockwise direction and that phase is acting like a south pole. If the current is moving in anti-clockwise direction and that phase is behaves like a north pole. So from this one it is concluded that the circular loop is behaves like a magnetic dipole and depends on the current direction, and one time if it is clockwise direction and that phase is behaves like a south pole, if it is anti-clockwise direction and that phase is behaves like a north pole, and finally that loop behaves like a magnetic dipole. That phase behaves like a magnetic dipole. So once again, all of you see the expression part. The current loop as magnetic dipole. The current loop as magnetic dipole. For this one, I am taking the equation, the exponent of the magnetic field at a point on axial line due to this is circular loop. The total diagram you already know in the previous classes. Now finally we got equation V is equal to mu naught by 4.2 2 pi ni r square by r square plus x square whole power 3 by 2. But here one condition I have to take. What is the condition? If this axial distance is much greater than the radius, then you can neglect the r. Then finally it will be 2 pi ni r square by x, 2 to cancel, it will be x cube. But here in this equation, the number of loops is 1, and in place of this I into pi r square, I can use m. And finally I got B is equal to mu naught by 4 pi into 2m by x cube. This equation is similar to electric field due to electric dipole, and there we are using P, but here we are using m. There the P stands for electric dipole moment, and here the m stands for magnetic dipole moment. And what is the m? The m is nothing but product of current into area, and the units are ampere meter square. And finally the direction, according to the direction of current, and the phase behaves like a, if it is clockwise current, the phase behaves like a south pole. If it is anti-clockwise current, the phase behaves like a north pole. And the next one, the magnetic orbital dipole moment of revolving electron. The magnetic orbital dipole moment of revolving electron. See, in any atom, the central part is nucleus. The central part is nucleus. Nucleus contains protons and neutrons. And here the electrons are revolving around the nucleus in a circular orbit. Electrons are revolving around the nucleus in a circular orbit. Now, if the electrons are revolving in a circular orbit, suppose if the electrons are revolving in anti-clockwise direction, but the conventional current is moving in clockwise direction, because the conventional current direction is opposite to that of movement of electrons. Now here the electrons are revolving in a circular orbit, definitely centripetal force will come to act. That centripetal force and coulombic force both are balanced. Now if it is revolving in anti-clockwise direction, the conventional current will be moving in clockwise direction. Now first we see from Bohr's postulate, the angular momentum of this electron is given by L is equal to mvr. From the Bohr's second postulate, L is equal to mvr, or Vr is equal to, I can use L by m. This I am taking as equation 1. The angular momentum of revolving electron L is equal to mvr, or Vr is equal to L by m. Now the current of this electron is given by I is equal to E by T. This is equation 2. What is the time? Time T is nothing but 2 pi R by V. This is 3. Substituting time in equation 2, then we will get I is equal to EV by 2 pi R. EV by 2 pi R. This I am taking as a equation 4. Equation 4. Now by using these equations, now we can get the magnetic orbital dipole moment of electron. How can? The magnetic orbital dipole moment, I can use the letter mu L. The mu L stands for magnetic orbital dipole moment, and it is nothing but a product of simply current into area. Nothing but I into A. In place of I can substitute this equation, that is mu L is equal to I plus EV by 2 pi R into, in place of area I can use pi R square. Pi cancel, R cancel, and finally mu L is equal to EV R by 2. EV R by 2. Or in place of VR, I can use L by M. So mu L is equal to E by 2 into, in place of VR, I can use L by M, and finally I can get mu L is equal to E L by 2M. And this is called as magnetic orbital dipole moment. Magnetic orbital dipole moment. So once again, all of you see the derivation part and equation, everything. See, when the electron is revolving around the nucleus in a circular orbit, because of this moment of electron in a circular orbit, whether this atom is behaves like a dipole or not, so that thing we can get. Central part is nucleus. Nucleus contains protons and neutrons, and the electron is revolving around the nucleus in a circular orbit. Now, if the electrons are moving in anti-clockwise direction, the conventional current will be moving in clockwise direction. And because of centripetal and electrostatic, it takes the circular path. Now, first, from the Bose-Einstein postulate, the angular momentum of this electron we can get L is equal to mvr. Angular momentum, mass, velocity, and radius of the orbit. And Vr is equal to, it will be L by m. This is equation 1. The current of this electron is given by I is equal to Q by T, or I is equal to, in place of charge I can use E by T. The time period you can get circumference 2 pi r by V. Later substituting, I can get I is equal to EV by 2 pi r. And later the magnetic dipole moment I can get by using the equation mu L is equal to, mu L stands for the magnetic dipole moment. It is nothing but product of current into area. So in place of current I can use EV by 2 pi r into area pi r square, and I got EVR by 2, E by 2 into, in place of VR I can use L by m, and finally I can get mu L is equal to EL by 2m. And from this result I can get two more results. What are they? See, gyromagnetic constant and Bose magnetron. Those two values you can get from the equation. See, first, mu L is equal to EL by 2m, or mu L by L is equal to E by 2m. E is nothing but charge. The charge I can write like this: 1.6 into 10 to the power of minus 19 by 2 into mass 9.1 into 10 to the power of minus 31, and finally I can get 8.8 into 10 to the power of 10 coulomb per kg. And similarly here mu L is equal to EL by 2m, and R E by 2m into L is nothing but NH by 2 pi, and H stands for 6.6 and 10 to the power of minus 34, and E stands for 1.6 into 10 to the power of minus 19 by 2 into mass 9.1 into 10 to the power of minus 31 into N is 1 into H 6.6 into 10 to the power of minus 34 by 2 into pi value 3.14, and finally I can get 9.27 into 10 to the power of minus 24 ampere meter square. And see, both are simply mathematical values. See, the gyromagnetic constant, and I can get from the magnetic dipole moment result. What is the magnetic dipole moment result? Mu L is equal to EL by 2m. EL by 2m. This L I am taking here. This ratio I can call it as a gyromagnetic constant. Gyromagnetic constant. E by 2m. What is that E stands for? E is nothing but charge of the electron, and m stands for mass of the electron. Charge 1.6 in 10 to the power of minus 19, and the mass 9.1 in 10 to the power of minus 31, and finally this 8.8 into 10 to the power of 10. This 8.8 into 10 to the power of 10 is called as gyromagnetic constant. And similarly, what is the meaning of this Bose magnetron? Mu L is equal to, once again I am taking the same result, EL by 2m, E by 2m, and in place of L, once again I am using the Bohr's postulate. The angular momentum of electron is equal to n times nh by 2 pi, and that I am using nh by 2 pi. Bohr's is first orbit. First orbit means n is equal to 1, and you can get EH by 4m pi. EH by 4m pi. E charge 1.6 10 power 19. H Planck's constant 6.6 in 10 power minus 34. It is a m mass by constant, and after substituting and everything, and finally I can get Bohr's magnetron value 9.27 in 10 power minus 24 ampere meter square. And these two constant values are important for 1 mark and 2 marks point of view.